it soon. Trees, we won't spend a lot of time on trees. Because trees are like very, very close. Okay. Okay, people are getting tired. Please don't be tired. Tarry with me. Okay. I'm connecting. Okay. Sorry, it's still loading. Okay. Anybody can see my screen? Ready to go? Ready to go?
Yeah.
Okay. Trees. Right? Trees are also need-based data structures, just like linked lists, right? So just like this, right? And they are stored in memory, just like linked lists are stored, right? So if you remember, we said linked lists, the advantage is that you can store the nodes anywhere in memory, right? You can store the nodes anywhere in memory, scatter them, right? Like, I hope you all remember. You can store one node here. I can store one node here. What is it? You can store like one node here. You can store one node here. You can store the data like anywhere in memory, scattered like this, right? But what matters is that there's a connection between them. And for linked list, the connection was the dot next, right? If you doubly linked list is dot next and dot previous, right? I hope you all remember that, right? With linked list, this is the dot next property. Do you all remember that? Do you all remember?
Yeah.
Okay. Trees are the same thing, except for trees, their length is different. Their length is just maybe if you are doing binary trees, let's just do regular trees. This is called child, right? This is called child. So like child. So if I have a tree property like this, a tree structure like this, it looks something like this. Like there's one node, which is this guy, the parent, let's call this one, and it has children, right? Like this, right? So like 2, 3, 4. So this is basically what the tree is. 2, 3, 4, right? Now if I translate this to code, we're going to have a node, class node, and we define what the node usually looks like. So we said for every node, there's the data, the actual data you care about, the actual data you want to store. They only call value. So like here, the value is 1, which that's what we care about. And then pointers to its to its children. For you're going to call it its children. But then it was like its next node. They're going to call it its children, right? Its children, right? Its children. And here its children, I want to make it a list of nodes, right? A list of nodes. So can you feel recursion happening? Can anybody feel recursion happening here? You cannot feel it. I'm so sad, right? Like, look, we're defining node, right? Can you see we're defining node? Say a node has a value and has children, and its children are also nodes. Can you see? We're defining node. We're still talking about node here again. Can you see the recursion here? Sometimes you say yes if I continue, else I not continue.
Yes.
Good. I'm very petty sometimes. So that is how a tree looks like. Okay, so it has a value which we care about, and it has a list of nodes. Please know this, right? It's very important to know, right? And each of each children is also what? It's also a node, right? So we're going to focus more on binary trees. Binary trees are simply trees. So we're going to talk about binary trees. Binary trees are simply trees, right? Whose children, the length of this children, list is less than or equal to 2, right? So that means that the node will have 0 child, 0 child, I don't know what to say, 0 child, 0 children, 1 child, or 2 children, right? That's what a binary tree is. It's simply a tree for which the number of children are at most 2. Everybody agrees, everybody understands. Are we good for everyone? That is number 1. Binary tree, the length of the children is less than or equal to 2. Does it make sense to
Yes.
everyone?
Yeah.
Like, we are there. Number 2 things I want to talk about trees, right? Like number 1, we have what we call binary trees. Number 2, trees, this is very important. You have to know this, are acyclic, whatever you want to call it, acyclic. That means there are no cycles in trees. There are no cycles in trees. There are no cycles in trees. This makes sense when we do graphs. We all know what cycles are because we started with cycles today, right? This is what we call a cycle, right? This is what we call a cycle. There are no cycles in trees. That means that if A is a parent of B, right? So A is parent of B. It cannot be that B is a parent of A. It cannot be. Does that make sense to everyone? Does that make sense to everyone? That this is not possible.
Yeah.
Please, does this make sense to everyone? Okay. It's important, like it's a good term to know because sometimes it's a technical discussion with the engineer, right? And these are the fundamentals that you know. There are no cycles in trees. Okay. So that's like you can get, like if you see something like this, right? and like somebody's like this not a tree. Like, but now there's a cycle, right? It can go from here and then here, then you come back to the root node again. No, there's no cycle in tree. Okay. The next one also is that trees are connected. Trees are connected. So what I mean by trees are connected. Please, all these things I'm listening here are important. Trees are connected. What does that simply means is this. That means that starting from the root node, which we call the main parent, the root node, you can reach every other node in the tree. You can get to every other node. It doesn't matter whether it's binary tree or whatever tree, whether it's an n-ary tree, like n-ary tree, a tree with, you can always reach every node starting from any node. It's not even just from the root node, starting from any node, you can reach every other node. Right? And if you look at this carefully, it is possible, right? Like if I look at this, like if I start from this, let's say I want to start from this node and get to this node, right? I can always get there. I can pass here, follow me. I can pass here. Can we all see this path? I can pass here, then I'll pass here, right? It's connected. Connected graph or connected tree means that from any node, you can get to every other node, right? That's what connection means. Does that make sense to everyone? Trees are connected. If assuming that, I tell you, this is how my tree is. Let's assume this is the space, right? And I'm like, and I tell you this is a tree. This is not a tree because I cannot get from this guy to this guy because there's no connection. Does that make sense to everyone? Trees are always connected. Are we good?
Yes.
Number 4, the last point I want to touch on. Trees are undirected. And this will make sense when we do graphs, God willing. Okay, are we good to proceed? Now, I'll focus binary trees. Shall we proceed? Are we good to go?
Yes.
Okay. Now, binary trees. You learn these things well once and for all. Like I learned them like once or twice for like, yeah. Okay, binary trees. What's binary trees? Anyone? What's binary trees? What's binary trees?
That has 0 and 1. A binary tree is a tree that must have the left child.
At most
and the
2
right child.
children.
At most 2 children, right? Just as Simon was saying, right? The length of the children is less than 3. Okay. So what is at most 2 children? We are software engineers. We are computer scientists. If at most 2 children, instead of saying we already defined the structure of a tree as this, right? A value and a children, we know that this length of children is bounded. It's at most 2. We are like, forget this. Let's make them left and right. So class binary tree node. So for a binary tree node, our tree node definition is value, left, and right, right? That's what we're going to do. We're going to call, so these are the children, the left and right here are the children. What did I just do? Left and right, right? These are the children we care about here, right? Okay, so this is a structure, binary tree like this. Now, let's switch our GS a little, solving questions with trees. Now, number one. This is a tree, true or false? A tree with 3 nodes, true or false?
True.
True. Next thing to know, this is a tree, true or false?
True.
True. 1 node forms a tree. Multiple nodes form a tree. You can have a tree with 1 node. It's still a tree. Just like linked list, you only had access to the head. For trees, you only have access to the root node, unless the question is different. You only have access to that root node, right? So if I just give you 1 node, the same algorithm you're going to apply to that multi-node tree, the same algorithm can apply to that single node tree. I think there's something probably confuses people. When they just see 1 node, they're like, is this a tree? Yes, it is a tree. 1 node is worthy to be called a tree. Its left is none, its right is none, but it still qualifies to be a tree. Comprenez-vous?
Oui.
Okay, let's move on to the next big thing. The next big thing is that given this tree, I'm jumping over it because you're supposed to have watched the videos and everything. So you're not going to spend time. I just want to mention something which you come across when solving questions. Next thing is now, given my tree, right, I want to be able to do something to this tree. I want to be able to print the nodes in my tree. So if you look at the schedule for this week, I wrote what we call tree algorithms. And one group I cared about was what we call the traversal algorithm, traversal algorithms, right? So for traversal algorithms, we're going to consider 3 main, should we make it 4? Let's do 3. 3 main tree traversal algorithms. The first one I'm going to consider is a pre-order. That would probably be the first. Then the next one is a in order. The last one is what?
Post order.
Post order. Okay. And we mentioned this when we were doing the that question. What was it? The evaluate reverse Polish notation, right? I mentioned these things, right? For instance, if you have 2 plus 3, that's in order. You have plus 2, 3. That is pre-order. You have 2, 3 plus. Some calculators process numbers this way. That is post-order. Same thing as trees, right? So if I have a tree like this, right, one now prints out the values of the nodes in a tree. Now, my number one hint I give to everybody solving tree questions is this. Whenever a question it involves trees, my algorithm is my suggestion to you is that write your algorithm as though number one, you are solving it for a tree consisting of only one node. What would you do? What would your algorithm look like? Then number two, write your algorithm as though it's a tree comprising of 3 nodes. If you're able to get your algorithm to work for these 2 cases, I believe that you should be done with your question, right? So we're first going to tackle pre-order. Let's do pre-order, right? Let's do pre-order first, right? Okay, so first of all, if I ask you to write pre-order traversal of a tree, think about this first. If the tree has 1 node, what will my output look like? What would it look like? Anyone? How will it look like? Also, if I just do this one, it means the left is none. We're going to present none with n and none with n, right? So with 1 node, that means that the left is none, right? Let's put n and the right is none. Does that make sense to everyone? What I just did? I'm using n to just represent them. Does that make sense to everyone?
Yeah.
Okay. Okay, we can bring L and R at the end just to make it make sense to people. Okay. So now let's focus on this 1 node. So when I do pre-order, right, on a tree with node 1, what should the output be? Anyone? What should the output be? Someone give me a guess. Even if you don't know pre-order traversal, give me a guess.
I'm gonna get
Mhm.
1
Mhm.
and NR.
1, what comes next?
Then the left node.
Usually we process left before right? Right. So this pre-order traversal. Pre-order traversal means that the current node, I'm pre-order traversal. Pre-order traversal means that the current node, right? So this is pre-order. This guy here is I want to use a different color. This is pre-order. Oh, this pre-order here, right? It simply means that, so here, pre-order, the operation here, that plus you see here is basically the current node, right? Pre-order means that the node itself should come first, then its children should come next, right? So pre means first, pre comes first, right? Okay, so you're going to have 1, then the left, then the right. Again, we process the left before the right, generally. Okay, now what about in order? Anybody give me in order? So this pre-order, in order. What does in order look like?
Left, the node, and then the right.
Okay, right, left, then the node itself, then the right. What about post order?
Post order is
The right, then
left, right, correct.
Left, right. I hope everybody is convinced by this. Everybody knows what pre-order, post order means now, right? Okay, that makes sense to everyone. Now, so you realize that when you just consider that 1 node thing, it's easily peasily, right? It's so easy. It makes so much sense, right? Okay, now let's apply that same. Let's focus on pre-order now. As I said, let's focus on just pre-order. Let's apply pre-order to this guy here. It's very important. Like if you're not, you have to be able to tell me what the output will be. I've been in like at least 2 interviews or so where the algorithm, where the questions was just like tree traversal. I'm not kidding you. Because many people don't know it. But here you are knowing it more, even if I teach you. So I'm going to call this one L1. We're going to call this one R1. We're going to call this one L2 and R2. So somebody help me. What does pre-order look like for this? Take your time. Don't worry, take your time.
1, 2, left.
Then give me a second. Let me take my. So everybody can put in the chat. Okay, let's just focus on the numbers. If I do pre-order traversal for the numbers, what should it look like? Just the numbers. What should it be? Just the numbers.
1, 2, 3.
Forget the NaN nodes. What should it be? Pre-order. Put in chat. Let me
1, 2, 3.
Somebody said 1, 2, 3. Okay, many 1, 2, 3s. Okay, it should be 1, 2, 3, right? Okay, that is correct. I hope you all agree, right? Okay, now let's include the nums. Everybody try. Take your time. Look at this. Take your time and try it. You've been able to do it for this case. Look, what you just did was a case like this. 1, 2, 3. This is what you did, right? Now apply it to this big case here. It's a challenge. It's a mental challenge I want everybody to try for your own good. Take your time, look at this and try it. It looks recursive, of course it is, but take your time and give us the answer. Everybody try and put in chat. Try it too for your own good. Are we all done? No. Please, I need more than this. Come on. there are like over 35 people on this call. Like, do yourself good. Take your time and try this. I need you to try this. Okay. Okay. Yeah. Thank you for trying. Okay, now let's proceed. Now we're going to do an exercise. I beg you, please everybody focus. Okay. So somebody tell me, what will be the first node to process? Somebody tell me.
1.
Node.
The
First
root node.
The root node, right? Which is what? 1. Because look,
1.
what we said. We said for pre-order, you never forget. You never forget. Pre-order. We said it is a node. Then you go where? Left. Then you go right. We all remember this pattern, right? Node, left, right. Pre comes first. Okay. So now let's start. So which one do you process first? Node. So what do you process first? 1, right? Okay. So we have 1. So then where do we go?
2.
Then we go to one's left, right? What is one's left? 2. Now, can we see? That's what I said. Look at this. Please look at this carefully. I want to change color. Give me a second. This whole thing is a tree. Do you agree? This whole thing is a tree here. You can all see that, right? And also, this thing here is also a tree. Can we see it?
Yeah.
It's
Yes.
a subtree. It's also a tree. So that same pre-order algorithm we are applying to the main tree. We're going to apply that same one to this subtree. Comprenez-vous? I know why my French has come today, but like, do you understand?
Oui.
Good. Those of you who didn't take French seriously because your French teachers used to cane a lot. They're looking at you. Okay, so now we come down, you come to apply the same pre-order algorithm because we came to one's left, and one's left is a subtree. So apply the same algorithm to one's left. So now assume that the tree you're actually working with right now is this guy. Assume this is the tree you're working with. So now, what node should we process next? From 1. We process 2, right? As you rightly said. 2. Can we proceed?
Yeah.
Okay, now we go to 2's left also. So we are here. 2's left. Is this also a tree? It's a tree. Is that the empty tree? Right? So, but then it's like none, right? And then we just put our NL1. Are we good?
Yes.
Okay, so for this tree, we've processed the node, we process the left, and now we come to its right. Can we all see it here? For that one tree, we processed the node. Where's my thingy? For that one tree, we process the node, as you can see here. Within the left, that is what brought us here. Now, pre-order says, where do we go to? We go to the right. So we come to NR1. Can we all see it here? You do the node, you do the left, you do the right. Can we all see it? Yeah, we can. Okay, so then we do NR1. Can we all see what is happening? Hello, people of planet. Inhabitants of Earth. I hope we can all see. Okay, now, where do we go to next?
Now we go to the right of the root node.
You can see that we are still back to pre-order. It's just like a recursive thing. Now, for this tree with root 1, we are then processing its left subtree, and that is this left part. We first processed the node itself, that was this one. We process its left subtree. Now, what do we go to? Its right subtree. Can we all see there? So, the full combination, tell me the whole thing.
So now we go to 3 and L2 and R2.
L2, then NR2. So that's the solution. Are we all convinced? Are we all convinced?
Yes.
I want to ask a question here. My question is like, so in this tree, once by this pre-order, the root is 1, then we go to the left, then 2 automatically becomes the root. We process its left again. Since there is no more child again, because of its pre-order roots left, right, then we now go to the root 2 of its right. Then after finish processing, we return back to root 1.
Right? Then you come here.
Yeah, come back. Then the same thing, root 3. We'll go to the left of root 3. Then we check. There's no like child root. We'll now go to the right.
That's all we did. Makes sense to everyone. Challenge number 2, because I'm bored. Do in order for this. Do in order. In order. Everybody, in order. Somebody has done it. But everybody, please don't copy. Those who used to copy. Please don't copy. Everybody do in order for this. You have to know this. Like, you have to. Like, some of those things have to be on your fingertips. Like, it takes time, but take your time. Everybody do in order. Please try. I beg you. Everybody try this. Like, try in order. Okay, in order. Everybody try it. You're helping your own self. Please, let's go. Let's go. In order. Take your time. Try it. Try it. Try it. Yeah, it's a bit small. It's a bit more not so intuitive, right, compared to the other ones. But like, yeah. Okay, try it. Try it. Okay. What's the formula for in order? Node. Oops. Sorry. Left. The node is in the middle, right? Okay. Somebody give me your answers. Quick, 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 quick. First person to talk, we'll take yours. We'll conclude yours is right. Somebody, quick, 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 quick.
NL1
Mm-hmm.
to NR1,
Mm-hmm.
NL2
Are you sure?
3, yes.
Are you sure?
And
This is
of
the left,
one,
right?
so yeah,
One has to be.
NR1 1,
Uh-huh.
NL2
Mm-hmm.
3,
Okay.
NR2.
Yeah, exactly. That's right. Right. Oh, we have got that. Yeah. Okay. Can we move on? So these are traversal things. You have to learn. I hope by now, this week, that's what you did. You mastered the algorithms. You have to master every single one of them. And see, this is a beautiful thing about recursion. Like, if I look, like you never think if you're supposed to implement in order traversal, def in order, or pre-order, any of them, def in order. You gave me the roots node. Base case, if not roots, what do I do? I just return, right? For trees, base case usually is the empty tree, right? Just return the tree. Then let's assume I'm printing them out, right? I'm going to print them out in order. What do you do first? You process what first? Someone help me. What do you process first?
The left.
The left. So call in order on the left. That is roots dot.
Left.
Then what do? You process the node itself. Here, we're going to call process print, right? So print roots.val. Then what do? In order on what? Right.
All
And
right.
this is the whole algorithm. We're done. Is it like it's just like the English you wrote here? Left, go left, node right. Call the function on the left. Process can be print, whatever it is, whatever the function wants you to do. Then call the function right. And that's the whole algorithm mode. That is the whole thing. Easy peasy. Some like trees, you have to learn it. Pre-order is simple. Pre-order, just move this guy. Pre-order is same as take this guy here, move him here. Post-order, take that guy, move him back here, and you're done. That's the whole algorithm. But please try to learn it, try to solve it iteratively too. It's good to know the iterative approaches. Try it, learn it. Yeah.
Please, the in order, I don't know how it works. I'm still trying to understand. Do you mind showing me, like the picture? Like go back
Yeah.
to
The
drawing code, the structure.
visualization.
Not like I want to understand how the in order goes.
Oh, how they
I was
work.
yeah. I was trying to
Okay,
visualize.
let's do that. Yeah, we can do that very quickly. So what is the formula for in order? Left node root, right? So we are here. We're like, no, go to the left first. The two is like, no, go to the left first. So you do the left first. So like it's like, go out till you get to the end first. Process that guy first. After you've done this guy, that is the left first. Now come to the node itself. Now go to the right. You're done. So that is for the subtree. So you're done processing this whole left. Now, come back to the roots now. That is a node. Go to it, process that node, now go to its right. When I come to this right, it's a node 3. It's like go to my left first. Go here. All right. Then come to me. Then go to my right. That's how it looks like. It takes time, but let it, marinate. Like think upon it and yeah, it begins to make sense. Okay. Next, I'm just going to mention it. There we go. Please solve the 3 questions. Like sit down, I beseech you. Solve them like struggle with them. After you look at the other solutions, like let's be a part. I cannot teach everything here. I can't. As much as I would love to, I can't. And some things take time for you to settle in your brain. Solve these questions. Please solve the questions, learn them. Next one, binary search trees. We are going. Binary search tree. It's simply a tree which is binary and we can search through. I'm kidding. Anybody, what's binary search tree? Somebody help me. What's binary search tree? It's just one invariant. What's binary search tree? So we know it's a binary tree, we all know. But what else? What's that special condition?
So
values to the left Like, let's say, I mean, the left child should be less than the parent,
Mhm.
and then the right child should be greater than the parent.
Okay, please, this situation, please listen to me carefully. Like, let me put my pencil down and talk. This condition we have here must hold for every single subtree in the tree. Every single subtree in the tree. Okay, so an example, 2, 1, 3. Is this a binary search tree? This is the last part that we are done, okay? Those who are tired, we are almost done. Is it a binary search tree?
Yeah.
Yeah.
Okay, please, we are doing quiz now. Focus. Okay. We are here. We're almost there. Almost there. Focus. Follow me carefully. Almost there. 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 And come on, if I'm not tired, please don't be tired, okay? Don't be tired. Don't be tired. Okay. Can you see are the circles too small? You can still see it. You can see, right?
Yeah.
Yeah.
Sorry, this is supposed to be 8. I beg, take your time. Take your time.
What don't us do this calling us?
Then I'm to tell me if it's a binary search tree or not.
So,
So this is a quiz. A, B, C. Please, for A, please take your time. Don't rush. Put in the chat. We're just doing A. Please take your time. This is the last thing we're doing. Then maybe a few remarks, things like that. A, is it a binary search tree? People already told us that for a binary search tree, I'm not even going to even remind you. Remind yourself. A, please everybody put your answer for A. Only A. Everybody put your answer in the chat. Let's do only A. Please don't put B so that others don't feel pressure to think ahead. Okay. Do you agree A is false? Somebody unmute yourself and tell me why is A false?
A is false because when we look at the node is 8, to the left is 2, so that condition is working. But then to its right is 5, so the condition doesn't hold there.
Okay, so that's one place, right?
Yeah.
And we got that. Anybody else? We are still on A. What else?
The 0, 2, 5 and 0.
Okay, here 2 is broken, right? So like it's broken left and right center. Okay, let's come to B. Answers for B in chat. Answers for B. Answers for B.
Yeah, I guess.
Let's put our answers in chat for B.
B, yes.
B is yes. Somebody why yes?
I don't think B is a binary search tree.
It's not.
Yeah.
I'm sorry, I want them to explain, but I want to laugh. Why is it not?
Because of the 7.
Yes, I put my pencil and I told you the condition must hold for every single subtree in the tree. What is the root node?
What's hiding?
8. Everything to the
Yeah.
right of 8 should be bigger than 8. True or false?
True.
Is it 7 to the left or to the right of 8?
It's to the right.
So this 7 is wrong. You can't have 7 here. Does that make sense to everyone?
Yeah.
Please, everybody should
Can
understand
you
this.
go over that?
Okay, so we all know the condition for a binary search tree, right? We're all good with that, right? I hope we all know the condition. Left must be less than node, right must be greater than node. We all know that, right?
Yeah.
Okay. Then I put my pencil down and I said, this condition must hold throughout the tree. Like it must hold like for every 2 nodes you compare, it has to hold, right? Does that make sense? So now look, if I take this 8, if I compare 8 to 15, it holds, right? 8 to 5, it holds. Do you agree? If I compare 15 to 10, it holds, right? But if I compare this 8 to 10, it must also hold. Because this 10 is still to the right of 8. Don't let this diagram fool you, right? 10 is still to the right of 8. Can we all see it?
Yeah.
But again, it holds because 10 is indeed bigger than 8, right? This 7 is still to the right of 8. Can we all see it?
Oh, okay. Okay.
But 7 is not bigger than 8.
Yeah.
Please, is everyone if you're not, take your time, look at it again. As you look at it, people, let's do for C. C, put in chat. Is it a binary search tree? C. C, yes. Okay, you keep on. Are we done? They have stopped typing. I beg, type. Yeah, it is, it is. I beg. Now feel free to type. It is, right? As the condition holds, it's a binary search tree. You see, the condition holds throughout the tree, right? So don't just compare just the recent, the immediate node to node. Compare for the whole structure, right? And that's it. Now, before you go, which one was a binary search tree? The C, right? Write in order traversal. That's the last exercise. Write in order traversal for me. Ignore none. Ignore now. Like ignore that and we used to do. Just write only the numbers. Write the in order traversal for me. Please, quickly. That's our last exercise. Oh, shoot. Our thing is done. It says I cannot write anymore. Shoot. Okay. It's that thing here is 10. So please write the in order traversal for me. Everybody try in order traversal. In order, in. So left node, right. Everybody try it. Only one? Try it. Try it. Are you all done? No, I need more than this. I need more than this. Okay. And what do we see about this? Anybody, any observation?
Oh, it's actually sorted.
Yeah, it's sorted, right? Can we all see sorted in ascending order? Can we all see? And
Yeah.
there are many coding problems that just use this idea that whenever you do in order traversal on a binary search tree, the output is a sorted order. It's an assorted and ascending order. There's a lot of questions using this, trust me. There's a lot. Whenever you do it, it's going to give you the output in sorted order. So in order traversal is very popular, right? Because it gives you the tree, the binary search tree in a sorted order. Again, binary search tree, not binary tree, binary search tree. That is our end of discussion for trees. God willing, next week, we're going to do a bit more tree algorithms. I'm going to show you some code for you to marinate in it. But again, we're supposed to do trees this week. So if you've not mastered it, if you've not sat down, I hope you have good appetite for trees now. You have God willing today, Saturday, going tomorrow, Sunday to finish with this week's materials. Go look at the questions again, solve them again, marinate in them. Like, let me show you something. It's like when I say solve the questions, like, Charlie, sit down, sacrifice 4 days, you and trees, like solve them. That's why I did though, because some digital practice, you need your brain to pick up, right? Like I'll open trees like this, then I'll go banana tree. Look, it's even here, like according we just discussed though. It's still an exercise, right? Like you come, open this. Forget my C++. Hey, says register or login. Please give me a few seconds to sign in. Okay. Right, like when I was 7, like that, like I probably did this to show people last year. I think so. 2023. I've not solved it again because I know it. I may go and solve again. But even see, when I learned it at first, I solved it like 5 times. This simple algorithm. So that's what I do. In order means at the middle, right? So call the function on the left child. Assume the function works, right? We're doing the same assumption here. Assume the function works means that if I call the function on the left child, I'm believing it to do the good job, right? Call it on the right child is then after that, put it in the middle. So you can see my left, middle, right here. The same thing I was teaching you. Yeah. Solve the questions, And if you come here, where is the NEET code site? Pelactis. Let's look at Pelactis, right? The same thing. Invert binary tree. It's the same recursion strategy we discussed today. The same thing. Look at this question. I think the question that Philippa posted. Look at this. Look at this code. When I'm doing this question, I don't think code. What will I think?
And the one I posted was balance,
Oh,
balance line.
yes, balance. Exactly. I always want to teach the other guy to get the non-local thing. Look, they said reverse. Look at this. Using our recursion strategy, if you remember, assume the function works, right? Which means that, notice the input thing is a tree, right? The whole thing is a tree. But 2, 1, 3 is also a tree, right? I established this point at the start. Subtree is also a tree. So I'm like, oh, this actually inverts the tree, which means that, so if I take this tree, the left subtree should become the right subtree, but it should be like for every tree, like it should propagate down. So like swap 7 and 2, swap 1 and 3 and everything. I'm like, oh, assume the function works. If I invert, I will just invert the left tree. It will work. I'll invert the right tree to work. And after both of them have been inverted, so that's like, assume that down here has been inverted. Like, oh, then just flip them. Make the inverted right, the current nodes left. Make the inverted left, the current nodes right, and I'm done. And I just return the roots, and that's the solution. Just by assuming the function works. It's so easy, right? But as I said, you have to practice. Like when I first solved this question, look, I've solved this question like 20 million times. Look, I first did this in 2021. Let me see what the solution I wrote. This was, I probably copied this solution from somewhere. I don't think I was this skillful in 2021. Well, like, yeah, but you develop it, right? And like, then later I'm developed, like, yeah, that's how you do it though. Like, look at this correlation I've written here. So ugly. But you improve, right? So solve them, like marinating it, do it, balance tree. The same recursion algorithms we discussed and everything. Same tree. Look, you know, like almost all the tree solutions have the same format to look.
Give us your logins to your LeetCode account.
Mine?
So we'll see all your code.
Yeah. And like, yeah, and if you and I said you don't have a pattern of writing code, right? If you look at this, look at this. You can see the iterative approach. Same, this is the iterative approach. You see, it's so complicated. Know how to solve it. I've learned how to solve it, so please you to know it. But look at the iterative, look at the recursive approach. Hey, recursion, why? This is so ugly. We only do
Oh,
this
so when you say iterative, you mean like the BFS?
Using a loop. Yeah, using a loop, right? Like, I want to show you something. Like algorithms on trees are like, it's like the same thing. Like, it's the same pattern. Call on left. Can you see call on left? Call on right. Base case. Add extra logic. Here, the logic is the combination logic. Like, it's the same thing. That's why I'm like, sit down 3 days, just do trees together. Your brain will realize that. You realize that, it's the same code, like it's the same format. You don't think. I don't do 3 questions and think now. Like, look, it's like the same approach you'll be writing. Let's choose the Python one. Like, not the one day recursive. Forget this guy. We just want
DFS.
DFS. Hey, we don't have time for this guy. But like,
You skip.
it's the same thing, right? Like, call on left, call on right, combine. Call on left, call on right, combine. There's a few nitties that we will be pointing out here, but it's like the same thing. So please sit down if you have not, repent, ask for forgiveness if you already haven't, and start. Solve all these things. This is an algorithm you must know to solve. This algorithm, like it's a must know. I've had a question. I had an interview with one of the companies almost everybody here wants to work at. I had a question like this. Even though it was a binary tree, I did it by God's grace. My friend interviewed the same company. I mocked my friend, but this question I had that. He also wanted to do his, got the same question. Then he got the offer. Now he's making money, probably more money than I make at my current company. But I didn't accept that offer. But like learn the algorithm, like it's the same thing. See, call on left. As you can call on left, call on right. These things just here, some extra sauce. Their combinations that, but like, it's the same thing. So please sit down, like dip your head into trees. 3 weeks, 3 days. Those of you who practice today, tomorrow you're on holiday, you practice in 2 days. You are not doing yourself any favor. You sit down, marinate me. Look at me when I said 2020, I couldn't even solve this question, this easy question that I'm sure my fifth born can solve in the next K years. I couldn't even solve it, but now you say I can solve it. Okay, any questions? Oh, sorry, so don't go, I beg, don't go. Tax force gone this week. We're going like fast.
Wait, are we done for today?
You can stop recording, so I should the tax for next week.